Hello. This is a brief video recording of the paper Comprehension Without Competence. Of course, this is borrowed from the philosopher Daniel Dennett's phrase of competence without comprehension. He meant that in natural world, you have all those letters of different intelligent beings that are competent in some way, but they couldn't explain. For instance, bacteria has very sophisticated behavior, but they couldn't obviously explain themselves. In particular, the thing that we're going to discuss is why large language model can explain, but they cannot execute. All right, so here is a very simple problem, right? So which number is larger? And at the time of the writing, I tested both GPT-4o and Crowd. They both got the answer wrong. But if you instead ask it why, not why, I mean to explain how do we compare the two fraction numbers, they actually have a very correct algorithm explanations. Like you have to align the points and you compare from the left to right? And if you go on, in fact, you use the exact same examples to earlier to explain the algorithm and got this time correct answer. Now this is very peculiar. So in exact same model, you see two different behaviors that it can do teaching very, very well, but it does not execute by itself. Just a side note, right? So there are a lot of benchmarks for large language model, and those grade level math problems are the simplest one, right? One of the more simpler ones, at least. And we expect our children to get all those problems correctly. There's no children, no kids that I know of will come to complain to his mom and dad that I got this wrong because it's an out of distribution problem. I got some of the steps wrong, right? So this is very peculiar. This problem only occur when we subject those kind of human tests on machine, that it becomes an out of distribution problem. But this itself is kind of interesting. Why should we actually have this constraint? At any rate, large language model is extremely good at being a teacher. So recently, I actually made a self-paced course as a meta experiment to let large language model explain the working mechanism of itself. It's a self-teaching course, right? So itself was based on this funny notion that we humans are too complex, so complex that we cannot explain how we work. But large language model, all this this knowledge of how the model is being built, all these papers are public knowledge, and many of them are already in the large language model itself. So as long as you design the curriculum correctly and scaffolding all the knowledge points, in this course there are more than 70 knowledge points, the large language model can actually do a pretty good job to be a competent tutor. It has this huge advantage over human tutors, that is no problems, no questions are ever too stupid. You can always say, slow down and explain that better, etc. The other thing that is very, very good is to be deeply personalizable, right? Imagine we're doing AI literacy for different domains of students, like physicists, even philosophers, right? You can consider each student is essentially a Bayesian machine. You can use concepts that they are most familiar to explain a new concept. Now, these two things, no human teacher can be as good as AI model, right? And of course, you can do self-updating if you want to, and it's out of box, multilinguistic ready. Right? So it becomes a gold rush for a lot of companies and so on and so forth. Now, assuming that language model can explain the algorithm well, so what it has problem of executing. This is what I want to prove in this paper. So the computational, what I is what I call it, right? Computational split brain syndrome. Now, split brain syndrome is itself a neuroscience or neurological condition where the two halves of the brain do not coordinate. It turned out in a domain called the distributed system, you also have this problem, right? Imagine you have a distributed database and you have a master node within that distributed system. If the two halves of the system partitioned, then there's a master on each of the halves, and then you're going to suffer data consistent issues, right? So this is called a computational split brain syndrome happening in distributed system. Well, for deep neural network, like larger model, we're not talking about there are actually disconnections within the model itself, but still you have this functional-wise split, right? So execution and the explanation occupying different region of the neural network. We can imagine taking a MRI of the network and see where all those three different kind of form, which they all should arrive at the exactly same result. They differ, right? One is execution, another is instruction, step-by-step instruction, another is essentially the word form of that. What's happening there? There's the independent pathways, right? So you have instruction pathways, you have execution pathways. They are both doing kind of pattern matching, right? But over different kind of text, but they do not overlap. They live in different region of the so-called the brain, or rather the latent space of the model. Okay. So let's dive in why this happens. I start with some of the mathematical problems that we're going to discuss first. Okay, let's start with the input, right? So there is this loss function, right? Everybody familiar with this loss function. Now the network has a lot of parameters, but the embedding itself is another parameter it needs to optimize. Now if you look at each particular word or tokens here, it's only optimized within the context it's appeared, right? So for instance, a bank can happen in different sentences and so on and so forth, and all has different meanings for this context. So a meaning of a token is context dependent. This is not new actually. This is for word to vec, it's already there. But if you query a language model, so for instance, what is the most probable meaning of 9.11? It would say it's a day, it's a date, remembrance, a tragedy. That's presumably because historical events that happened. And 9.9 is a number, right? A decimal, but also encodes a perfect and high, which suggests it has some kind of prior that 10 is a perfect score, right? At any rate, you can see the larger model think of these two numbers in different ways, right? And this is really because each token is trained up by the different context, and that is the embedding needs to work for all contexts. So it works poorly for each one of them. So when we ask the question 9.11 and 9.9, which one is bigger? Essentially, we're asking it in the context of mathematics domain, right? So math domain, we should expect that the embedding should adhere to asymmetric property, meaning even though for us numbers on is 1D, right? You can see all the numbers line up 1D. We accept 1 and 2 and 4 and 5, they all distance with like 1 unit of distance. If we want to have it to operate on the mathematical equations, such a problem consistently, we should imagine or should expect when they project into high dimensional space, the distance metrics still adhere, right? That is clearly not the case. In the paper I did, there's some experiment to show that for the numbers, that distance is not even, right? So it's a different kind of distance matrix for different numbers. You can see 9.11 and so on. They have this kind of square correlations. and so on and so forth. You can find more in the paper. So that means, imagine you're doing a arithmetic problem. You have a calculator. When you punch into the calculator, you're expecting the calculator circuitry is receiving the same kind of, the number is expressed in the right way. But internal to the language model, unbeknown to you, they actually have different kind of position in the embedding space. So if your input is not stable, you could not expect that there are stable or input agnostic circuitry, right? So imagine you're doing a sorting, right? Right before you start the sorting algorithm starts, all the numbers, all the inputs are occupying in different kind of positions. How would you expect a sorting algorithm work, right? You would always operate wrong numbers. So even if you have perfect input agnostic circuitry, the very fact that the input is already kind of randomly, not entirely randomly, they're corrupted by their context, then the algorithm will not work. Now let's look at the other dimension, like assuming that your input is actually clean, right? Let's see what's happening inside the network, right? So this is everybody of the transformer would understand this. You have each layer of transformer has two components. One is attention, another is the feed-forward network, and so on and so forth, right? So if you are not going to go through the equations, but eventually what's happening is that you can kind of regroup the contribution of different components. Say, okay, so there's the embedding in this case is equal, right? And the attention, because the causal nature of the attention is looking at the operands and operations. Essentially, it's computing at different layers. No matter whatever the layer we're computing, the representation at that particular layer of the operation operand, right? And then finally, you have this feed-forward layer that contributing the another component, which is this one, right? Now, so what it means, right? So if you look at the optimization problem, right? You have the embedding, which is equal, right? And then you have the operation operand, which is what the attention the computing. The attention basically tells the model, here's the representation of this operational operators. 78 and 43 need to be multiplied, and the rest need to be figured out by the feed-forward network. Feed-forward network, because there is a universal approximation theorem, it can approximate any functions, but it turned out it's an approximator, right? It could not perform multiplication or any high order high order operations like exponents and log and so on. They would require second order interactions among the digits, right? So now, if you have a target to predict, right? So the target have a gradient coming back, and we know that the attention layer, however it's optimized, will just only tell you what to do, right? So the feed-forward network being a huge approximator and has about 2/3 of the parameters, what it does to nudge its parameters so that it can remember some of the results. What happens, you can see essentially what I call the residual fitting process, right? So each layer contributes some kind of memorized fragments, and gradually it will fit the target. So what that means? So that means if we put these two things together, there's no input agnostic circuitry, and you will always have out of distribution problems, because whenever it steps outside the region of the training, the model start to interpolate the results and finding the closest answer. So there's just no general computation here, right? All right. So that basically explains the computation is actually being approximated as a pattern fitting process, right? Now the peculiar things, right, is that you have a model that can explain perfectly the algorithm but cannot execute. So why it cannot kind of connect these two capabilities, right? So it can explain the algorithms, so why cannot use them? I think the answer is really simple, because for both of the instruction text or execution text. The language model, when it was trained, it has no idea, it doesn't really care what kind of text it is. For both, we're just nest token predictions, right? So there's no label saying that this is a instruction and this is the execution, and that the two has to combine, have to connect to each other, right? So they are just pattern completion tasks, and there's no mechanism to say that I use this instruction for execution, right, internally. So that's the experiment we have seen before, that it turned out those pathways are just independent. So larger model just does memorize instruction patterns, and there are, relatively speaking, bounded variations of those. That's why whenever you ask it to explain algorithm, it can explain this way or that way. It does a pretty good job. But the execution itself, in theory, they are unbounded inputs, right? So you can memorize execution patterns. Therefore, you would always have auto-distribution problems. Therefore, the competence not really there. Now, those two capabilities are parallel independent. So there's no use function to connect these two capabilities, at least not internally anyways. Right? So that's kind of proof for the multi-step algorithm arithmetic problems. So we have competence that is below the comprehension level. Now it turned out this is generalizable. Okay, so you have similar patterns for relational reasonings, right? There's this interesting paper that look at this, what they call the reversal curves, where you say Tom Cruise's mother is who and who, and you ask the reverse question. Turn out they collapse on the reverse direction, even though this is symmetric relation. Son of somebody and mother of somebody, there is it's a relation that is seen from different directions, right? And there's this another interesting problem called Alice in Wonderland problem, where you have the model was asked that Alice has 4 sisters and 1 brothers. How many sisters does the brother have, right? So at time when I was testing it, all those top models just fail. So I'm not going to explain this table in detail, but essentially, it's the same problems occur for arithmetic problems occur here in relational reasoning as well. That is, if to answer those problems correctly, you need to do recontextualization, right? So in this case, Alice is not some random people on the street. In this context, we were talking about the family relationship, right? The same way when we asked 9.11 and 9.9 comparison, we're talking about the purely arithmetic context, and we need to recontextualize and bind them to some variables. And then you use whatever the algorithm needed to infer them. If either of these steps are broken, in our case, if both conditions are broken, then we'll have issues, right? So in this particular case, in first case, the larger model was just memorizing A and A is B, and B is A is memorized separately, right? So what we really need is the lift reasoning, that we need to apply the algorithm bindings and the variable bindings, and execute them. So, okay, so what are the potential workarounds? So, well, one thing is for the model to access a query, and say if it's too difficult, right, it will just do self-scaffolding, which essentially unfold a multi-step algorithm into a sequential execution. Right? That's one way of doing that. Or you just compute call a tool, right, a programming tool, for instance. So the problem, rather the challenge here, is a metacognitive bottleneck, where the model needs to assess, which is the difficult queries to unfold, or to call a tool, and which tool to call, right, etc. And this self-assessment may not be robust, and that could be issues. Who watches the watcher? So there are many interesting research works out there. For instance, the illusion of thinking from Apple shows that the model would fail despite detailed planning. In this paper, we did a simpler but also illustrative experiment. where the model was given the golden scaffolding here, right? And the scaffolding here is totally fine. And it was the models all collapse, when the summation happens, presumably because it's out of distribution, right? So that's why I think the commercial models all default to tool calling for those kind of problems, which is a correct practice. That's the current status, right? So that brings us to this peculiar question. The larger model that we use every day, in fact, this paper and this talk itself are all helped by using cloud and GPT and so on and so forth, right? So if we zoom back, we can see that actually there's, let's broadly say, computers, systems like a database, operating systems, and a compiler, etc., or high-performance library, etc., is a system. And then you have machine learning all here, right? Before it was a larger model was just pre-trained model, but nowadays, as a larger model becomes so big, right? I just basically call it the world model. And the other machine learning model, I would just call them data models. Now, this larger model is so big, it overlaps with the data models, the other machine learning model, and sometimes the computer systems as well. So things that need to be computed by external tools, sometimes people mistaking it to let it larger models execute that. It's precisely those gray regions that's problematic. But still, it's very, very powerful. So how do we explain that they are so powerful? So I think that large model essentially are massive scale, multi-level pattern completers, right? At a human interpretable level, there are at least 4. You can complete a code, you can complete a text, so on and so forth. So basic, sentence completion. And at the very, very top, right? So for this large reasoning model, essentially you're doing, for any kind of problems, we need to decompose that. And then we try this path. If it does not work, we backtrack and then move forward. That's like a kind of also a pattern completion, right? It's at the meta level, which governs many timestamps. And in the middle, you have for a particular problem, you can solve that by multi-step chain of thought reasoning. Okay, of course, you can do instruct following. You can do brainstorming, writing email, etc. Those are also we can think of them as pattern completion problems, right? So larger model are just massive scale and a pattern completer, and they can switch between the levels very flexibly, right? And therefore, it's good enough for many data tasks, and they're certainly better than many human works already in the domain. I think the level of depth and the flexibility of the mix them is essentially, the expertise gap between a naive and a researcher versus somebody has been working on the field for many years. So what do we have? Okay, so my point of view, I think we can settle the debate of artificial general intelligence, and we just admit general intelligence is already there, because I think general intelligence day-to-day tasks just require pattern completion. But if you look at the complete cycle of scientific discovery, right? What we need to do is we should extract new algorithms, new laws from the observation, and then apply them reliably in the other direction. Right? In this talk, I'm just basically saying, even just apply to the known problems with known algorithms, we have reliability issues, right? And this generalizable intelligence needs to complete both cycles, right? And essentially, we need lifted reasoning. So we need ways to extract, do the inductive reasonings, right? This ArcAGI second challenge, essentially you would require recognize some common patterns and abstract them and then apply them back. It turned out at the time of writing the paper, the rule discovery task is the second challenge. The larger models are pretty poor, right? Despite the fact that the human can solve those easily, because we have this extract the pattern of the laws and apply this full cycle, and I don't think the larger model can do that today. So if we have a time machine and send large model back 500 years ago, which is before the modern science happens, it can answer any questions, and therefore we do not have the modern math and physics, therefore couldn't actually build a large model today. So that's a kind of paradox, that if large model exists many years ago, we may not have large model today. So people might think this is not as relevant, but consider this posed by capacity. Right? So one of the things that he observed is if you have codes that are essentially redundant, right? Larger model do not have the ability to recognize there's a need to abstract them into routines, right? So this is where the software engineering or the whole field come to play. You know, how to design your software modular and flexible and etc. It's a form of art. And a large model cannot do this just by itself. So another thing that we discuss in this paper is the implication of mechanistic interpretability, which is a very hard field, right? So there are sparse autoencoders and attribution graph. Those are wonderful work, and people seem to suggest they discover some features that correspond to human recognizable concepts. Now, one of the things this paper was suggesting that we might just recognize patterns rather than completion, rather than actually implement the algorithms. Right? There are many works cited in this paper that point otherwise. The paradox is that we comprehend what the features correlate with, and we make a correlation for computations, right? So, or reasoning for that matter. People talk about large language model being a reasoning engine, but are they doing reasoning at all, right? My suggestion is to really look harder and do rigorous auto-distribution tests. And one thing that I really particularly worry is that we often suffer from this confirmation bias. Right, we have problems we throw the large model at, and we then look for patterns that kind of explain that execution. And that is a form of confirmation bias, which is problematic. Right, we should really distinguish two types of finding. That one is pattern coordination, the other the computation procedures, which this paper argues what we discover is most likely the former, not the latter. So just to conclude, I think essentially we are expecting larger model to do something that's impossible, right? It cannot, in zero shot, complete a query that is in its very nature multi-step algorithms. And we need a rift reasoning, which is automatic binding of the certain variables of state in the right context, right? Adhere to the right properties, for instance, isometric properties, and then we have to have a faithful execution that binds to a algorithm. Neither of them, I think, is capable by the large model itself. Now, the peculiar thing is what made large language model so successful. There are many other important factors, but I just mentioned these three. That you have a single unified encoding scheme, right? It's an embedding space, right? And you have a very straightforward loss objective, Nernst token prediction. And you have this wonderful architecture, transformer architecture, kind of split the attention with a causal attention and also the feed-forward, which is a very powerful pattern storage, essentially. Now, all those are fundamental for the success of the transformer, but those are very successful, very factors are causing this computational split brain syndrome. So fluency in comprehension is not the same as a reliable competence, right, or computation. And the scale alone will not bridge this gap. Essentially architecture is destiny, architecture and the training paradigm, I should say. And finding stable circuitry level interpretability, I believe, is another mission impossible. That's just a very negative result, which I feel and I hope it was not true. because we have the brain and we cannot open the brain to understand. And now we have the larger model which we can open the skull and probe every neuron, but yet I don't think just by the very nature of how this artificial brain is made, we cannot find the kind of interpretability we expect to find. And I think there is a new form of hallucination, which is computational hallucination. So for any problem that's essentially multi-step algorithmic execution needs a multi-step algorithmic execution, you will always, if you do zero shot, you always risk the chance of creating hallucinations, right? I think that's a rule of thumb. So, of course, I think the really, I do not claim we have any solution. The point of this paper is to really decipher what do we have here, right? Is it really reasoning? Is it computation? If it's not, what are we building here? Only when we have this concrete understanding of what we have built, I think we can make progress. Thank you very much.